Hello, welcome back to ECE484, spring 2021, fall 2021. Okay, so we have been looking at direct design of digital controllers. This is where you discretize the plant using the step invariant transformation, and then you design the controller in discrete time. The advantage of doing that is that you can account for possibly large sampling periods and get performance guarantees, at least at the sample instances. We have been looking at, we've started to do state space approach to this direct design, okay? And we've started with the stabilization problem. In other words, how do we stabilize an unstable plant? Okay, the basic control problem, and then we'll build up from there. Okay, so we've got our system here, is our state space model. And we said that to solve the stabilization problem, we needed this notion of controllability. And then we talked about kind of what is controllability and how do we test for it. And basically, I've summarized what we've talked about in this little setup here. We said that every state is reachable for the system. In other words, you can drive the system from the origin to any other state in its state space, if and only if, where that's equivalent to A, B, the pair being controllable. That's the definition of controllability. In terms of a test, we talked about this controllability matrix here. And AB is controllable if that controllability matrix has rank n. Okay. We gave an alternative test, which was in terms of the eigenvalues of A, and that is, in words, that every eigenvalue of A is controllable. In terms of a mathematical test, it's another rank test. You take the rank of A minus lambda I, where lambda is an eigenvalue of A, and then you put beside it the B matrix, coming from the system model, and that matrix should have rank n for every single eigenvalue of A. Okay? And the image, or the column span of the controllability matrix, which was this guy here, is the set of reachable states from the origin. Okay? And so the rank condition above is simply saying that the column span of that controllability matrix is the entire state space. Okay. And from there, we continue. So from our point of view, the most important fact about controllability is the following. The most important fact about controllability is the following. Okay, and I'm going to state it as a theorem. I'm not going to prove it. It's something you typically see in graduate school. You would see the proof of this. So theorem 913. AB is controllable if and only if and again, in the context of our stabilization problem, this is why this is an important property for us. So the condition is if and only if for every set of desired eigenvalues, there exists a matrix, a state feedback, F, such that A plus BF, which remember A plus BF is the kind of the closed loop system after we apply the state feedback. So A plus BF has exactly the desired eigenvalues. Okay? So it's sort of like a state space version of our pole placement idea. Okay? And it says that, again, if AB is controllable, for any set of desired eigenvalues, I can find a state feedback, U equal to Fx, such that when I apply that feedback, the resulting system, which has matrix A plus BF, will have the desired eigenvalues. And so in particular, if I pick them all to be magnitude less than 1, I will have solved the stabilization problem. Okay, and so we make that observation explicit. So this result implies AB controllable means that we can solve the stabilization problem. Stabilization. Right? Just pick all your eigenvalues to have magnitude less than 1 and solve for f and use that controller. Okay. So let's do an example of exactly that. So I've been doing some examples not from the notes just because I'll give you some extra examples, I suppose, but I'm doing different examples. So this one is also not from the notes. And we have the following. Okay, and I want to stabilize this system. Stabilize this system via state feedback. So for that, in this case, there's two states, one input, so this is going to look like F1, F2 times X1, X2. Okay, so first let's check if we actually have to do anything. Is the system stable already? Because if it is, then just pick f equal to 0. So in this case, you can check that the eigenvalues of A are equal to -1, -2. So open loop unstable. Okay, so we're actually going to have to design an F. Okay. So let's see if, first of all, if it's controllable. If it's controllable, then we should be able to solve the problem. So first question you might ask is, does such an F, or does such a state feedback controller That's the first question, right? Is this actually possible? Certainly if AB is controllable, then yes. Then yes. So let's check if it's controllable. Now, if you think about an example we did last class, remember in last class we took a transfer function. We applied our transfer function to state space approach to get the resulting A and B. And we showed that in the general case, that AB is controllable. And we said, okay, it turns out that our procedure always gets a controllable system. And the form of that A and B matrix was called the controllable canonical form. So look at this system here. It has exactly that same form. Ones along the superdiagonal, some numbers along the bottom row in the A matrix, and the B matrix being 0 and then a 1 at the bottom. Okay? So if we go back to that example, you can see that this is just a special case of a controllable canonical form, i.e. this is the type of state space model you would get if you applied our transfer function to state space approach that we've talked about in this course. So I know it's controllable, but I'm going to just check it anyway. So I'll just say AB are in controllable canonical form so the pair is controllable. It was, I guess I would say, I didn't have a number. Like, I'll just say, see example from last class. So technically I don't have to check, but I'm going to check anyway. Let's double check. Okay, so I could use the PBH test, which we talked about above, or I could check the rank of the controllability matrix. I will check the rank of the controllability matrix in this case. Both are equally valid tests. So WC stops after the first AB term shows up because n is equal to 2 in this case. There are two state variables, sorry. B is 0, 1. And then A times B, well, let's do it. First row of A times B gives me a 1 up here. The second row of A times B gives me a 2 down here. Okay, I immediately see that the two columns of this matrix are independent. I can't write one as a scalar multiple of the other, so I know that it's full rank. The column span is going to be R2, but if you don't want to do it that way, if you want to be double check, we can, in this case, because it's a single input system, we can just check the determinant. And here we get 0 minus 1. Okay, no surprises there. Okay, so now that we know that it's controllable, we can go about and try to design the stabilizing controller, the F, right? So stabilizing F in this context means picking those two gains, little f1 and little f2. All right, so we're going to do that. Solve for F. Okay, and in this case, what we'll do is we'll just do it kind of brute force. First, let's pick where we want our eigenvalues. So say we want the eigenvalues of A plus BF to be negative 0.5 and negative 0.2. So in this case, I haven't put much thought into it. Really what I should be doing is I should be using the techniques we talked about in Chapter 8, right? I should pick good pole locations in the S-plane and then map them over using the exponential. But that's not the point of this example, so let's just say that these are the eigenvalues that we want, okay? Okay, so what we should do then, one way to do this, maybe not the best way, but one way to do this is to just look at the eigenvalues of A plus BF and compare them, or choose F, so that they are equal to these numbers. So let's do that. So in this case, A plus BF looks like this. I just plugged in A, B, and F. Multiplying this out, I'll do it extra. I'll take an extra step here. So there's A, B times F, looks like so. And so when I write it out, I get this matrix. Okay, so now the eigenvalues of this matrix are the roots of the determinant of Zi minus the matrix. So let's calculate that determinant. So recall that the eigenvalues of A plus BF are the roots of that polynomial, right? We talked about this in chapter 6 when we were looking at asymptotic stability, so this is something should be familiar to us. Okay, so I'm going to compute that determinant. And so in this case, we get so I've just did the determinant of Zi minus A plus B, minus A minus BF. Calculate this all out, and you will get Z squared plus negative 2 minus F2 Z plus negative 3 minus F1. Okay. So as just doing that straightforward calculations. Okay. Now we said that our desired eigenvalues are negative 0.5 and negative 0.2. So why don't we use those desired eigenvalues to generate a desired polynomial, just like we've done before? I'm going to use the same notation, in fact. So desired eigenvalues give okay, those are my, remember I wanted eigenvalues at negative 0.2 and negative 0.5. Multiply this out. And we have this polynomial. So now, in our simplistic approach here, we just compare coefficients. Here's our actual polynomial corresponding to A plus BF, and here's the desired polynomial. So the actual eigenvalues of A plus BF are the roots of this polynomial, and these are our desired eigenvalues. So we'll compare the two coefficients and get our values of the gain matrix. We get those two equations, which if you do the calculation, you get negative 3.1 and negative 2.7. Okay, so there's our first state space design. It's a state feedback which stabilized an unstable plant. And we were able to do that because controllability implied we can place or assign the eigenvalues of A plus BF arbitrarily. Okay. Now this worked out nicely in terms of the equation because A and B were in this controllable canonical form. In general, if you just kind of use this brute force approach, things can get messy. Okay. I will not cover kind of some of these techniques to do this by hand because in practice you would never do it by hand. But if you're interested, you can look in the notes. So I'll say C section 9.1.2 for two procedures for computing F to assign eigenvalues of A plus BF. Okay. I will also mention that MATLAB, of course, does this because those procedures that I'm mentioning there, they work well for small problems, right? Small problems you can do maybe two-dimensional, you can do them relatively well. But for larger problems, it's going to become tedious. And so, you know, for larger problems, you're going to end up using some sort of software. And so I'll just mention that in MATLAB, there are two commands. To generate our Fs. One is called place, and you give it a matrix from the system, the B matrix for the system, and a vector of desired eigenvalues. Okay. Or there's another command. Acker, it's called, for Ackermann, who came up with a formula for doing this calculation, and then that's one of the methods discussed in the notes. And so Acker will do the same. Will take the same sort of arguments. Okay. The negative sign out in front is just the convention. MATLAB wants to write it as a minus BF. I like to write it as a plus BF. Okay. But that's why MATLAB assumes that that your closed-loop system will be a minus BF. So it adds an extra negative. That's why I have to undo it by adding that negative out in front. Okay. Now, I want to remind you that this state feedback requires a sensor for each sensor, a sensor for each state variable. So it is not practical in general. So let's just make that very clear. State feedback requires a sensor for each state variable. And to kind of give you a diagram of what this would look like, consider the double integrator that we looked at last class. For example, for the double integrator, an implementation diagram might look like this. Okay, so let's draw what it looked like in the case of the double integrator. Okay, so first of all, we have our underlying continuous time dynamics. So let me draw a few boxes here. Okay, so our continuous time system is a double integrator. Right, it takes as an input u. You integrate u and you get x2. You integrate x2 and you get x1. Right? And so this block here is c to d of the double integrator. So I'll remind you that this is x plus okay, so there's that system. So now if we're doing state feedback, what we're saying is that we have a sensor that can measure both x2 and x1. And so what that would look like is, not only would we be able to measure x1 from the sampler, but we'd have to have an additional sensor here to sample x2. And then we would take x1 and we would take x2 and we would multiply them each by the designed gain. Okay, and so let me do that like so. So there's quite a few blocks, but bear with me. In other words, to implement this, we would take the sampled value of x2, and that would be multiplied by whatever gain you computed, little f2. And again, we would take the sampled value of x1 and you would sample, and you would multiply that by the gain that you've designed, F1. Right? And now those two signals, so this would be x1 of k, x2 of k, would be read onto the computer, of course, through your sensors. You multiply them by F1 and F2 respectively, and then you add them up together to get your control signal. So I will draw that over here. So this might look like, again, bear with me. Like the following. Okay, so what I've done is I've just multiplied them, added them together, and that generates U of k. And U of k is what is ultimately sent back to my plant. Okay. So this is what the implementation diagram might look like in the case of a double integrator. Of course, you have to pick the values of F1 and F2, but what you see is that it requires more sensors. And so we'll deal with that in a moment, but I wanted to just emphasize that in an example, right? Like this controller that we're using may not be feasible in some cases, or it might be too expensive, right? Maybe you can do it, maybe their sensors exist to do this, but you don't actually want to put those sensors there. Okay. So we've seen now that controllability allows us to solve the stabilization problem. In fact, controllability allows us to do more than just solve the stabilization problem. It allows us to place the eigenvalues of A plus BF anywhere we want. There's a related concept which is weaker than controllability, which is called stabilizability. And that is the true minimum requirement we need to solve this so-called stabilization problem. So a related concept to controllability is stabilizability. All right. And so the definition is the following. AB is stabilizable, or the system is stabilizable, if there exists an F so that A plus BF is stable. Kind of makes kind of a reasonable definition. And I want to point out that, of course, controllability implies stabilizability. Right? Controllability means we can place the eigenvalues anywhere, and in particular, we can make them stable. So controllability implies stabilizability. I'll write that down in a second, but let's do a little mini example here to show sometimes that what might go wrong. Now, think of this little mini example. It's clear here that the first state, x1, just evolves on its own. You have that x1 plus is equal to a11 times x1. And there's nothing I can do about the evolution of that by choosing the control signal. The control can't kind of get at x1, can't reach it. And so whether or not this system can be stabilized is going to depend on whether or not that first state is stable on its own. Okay? So let's make that even a little bit more clear. Suppose I take f equal to, as usual, f1, f2. Then if I look at the closed loop eigenvalues, I'm going to get the following. So the fact that the control can't get at that first state, can't affect its evolution in any way, the way that's manifesting itself is that this term here, my feedback has no effect on it. It doesn't matter what I pick for f. I can't do anything about the fact that in the closed loop, this system is going to have an eigenvalue at a11, exactly at the value of a11. And there's nothing I can do with the control to affect that. This other guy over here, I can make it whatever I want. I can make this second eigenvalue to be stable or whatever the case may be. But this first one is fixed. There's nothing I can do about this eigenvalue. It can't be moved, can't be shifted, so to speak, by any state feedback. Because it, again, the control sort of can't get at x1. It's clear what's happening. Okay? And so we have in this case, so in this example, AB is stabilizable if and only if this eigenvalue that we can't do anything about is already stable. If and only if the magnitude of A11 is less than 1. Okay? So this kind of illustrates the idea of stabilizability, right? We might still be able to stabilize this system, but it depends on sort of the part that the control can't affect. It depends on that already being stable. Okay? Okay, so in terms of testing for stabilizability, we use the PBH test again. So the PBH test can be used to test for stabilizability. Okay, and the result is the following. Stated without proof again. AB stabilizable if and only if every unstable eigenvalue of A is controllable. Remember that we said that an eigenvalue is controllable if it passes that PBH test, which was the rank of A minus lambda I B equals the dimension of the state space. And so stabilizability is basically saying that we just need that the unstable eigenvalues, in other words, the eigenvalues that have magnitude greater than 1, we need those guys to be controllable. And the intuition essentially is that we don't need to change all the eigenvalues of A to stabilize. We just need to be able to control the bad ones. So we only need to shift or move the unstable eigenvalues. And again, in the example above, it's saying that if this is already stable, then you just leave it alone. You don't need it. You don't need to change it to do stabilization. You have to make sure that the second guy is stable in that case. And so this test is, the intuition is that the eigenvalues of A that need to be changed are the ones that are unstable. And so those guys have to be shiftable or controllable. Okay, and so the last thing I mentioned before, controllability clearly implies stabilizability. But the converse is false. Okay, so let's do an example where we stabilize a system which isn't controllable, but it is stabilizable. This example is from the notes. Okay, so let's write it out. Okay, so here's our system, and we want to solve the stabilization problem. Okay, so just like before, what a reasonable or a principled thing to do would be to first check if the problem is solvable before trying to, dive in and try to solve it, right? Don't go off on a fool's errand. So as before, we could try to check controllability. Now, I will do that, but of course, in this example, I'm illustrating stabilizability. So if we expect, or you can expect that it's not going to be controllable, but it will be stabilizable. Okay, and then we will design our controller. So let's do what we would do normally. The first thing we do is we should check controllability. See, because if it is controllable, then clearly we can solve stabilizability. So we can check controllability. We check our controllability matrix. And if you do AB, what you will get is the vector 1, 1 again. Right? The first row of A is 1 plus 3, or 1 times 1 plus 3 times 1, so that's 4. Whole thing divided by 4, so you get a 1. And similarly down here. It's clear that those two columns are dependent, and so you're going to get rank 1. So not controllable. So we cannot arbitrarily change the eigenvalues of the closed-loop system. There's going to be some eigenvalues that are fixed, can't be moved. And for stabilizability, what we need to check is that the ones that can't be moved, hopefully they're already stable on their own. Because if they are, then we can solve the problem. If they're not, then there's nothing we can do. Okay, so let's check stabilizability. We said we're going to use the PBH test to do that. So for the PBH test, I need the eigenvalues of A. So in this case, the eigenvalues of A are negative 0.5 and 1, it turns out. Now, for stabilizability, what I want to be able to say is that I want to be able to shift this bad eigenvalue. It has magnitude 1, so it's unstable. So I don't care about this guy. I don't care whether or not it can be moved. It's already stable. What I want to do is make sure that I can get rid of this unstable eigenvalue. So I'm going to apply the PBH test to the unstable eigenvalue. Okay, so we need that this matrix have rank 2 for every unstable. Right? In this case, there's only 1. So we're just going to check it with lambda equal to 1. We only have 1 unstable eigenvalue. And so here we have so this is what we get. Okay, So say looking at the first column and the third column, you can see that they have, one has a negative sign, one doesn't. So they're going to be linearly independent. And so this is going to have rank 2. Again, alternatively, you can check the determinant of every 2 by 2 subminor, and if there's at least one with non-zero determinant, every 2 by 2 submatrix, sorry. Check the determinant of that 2 by 2 submatrix. If there's at least one with a non-zero determinant, then you have full rank. Okay, so the pair is stabilizable. So I'm just going to write this as the following. The unstable eigenvalue is movable. And so AB is stabilizable. Okay, that's kind of an intuitive way to think about it, right? We can actually move that bad eigenvalue. Okay, so in terms of design, actually, how do we actually design the F? The strategy is going to be the following. We know the system is not controllable, so I can't just pick arbitrary eigenvalues and solve for F. However, we know that the unstable one is movable, as I just wrote. So the strategy is going to be to pick our desired eigenvalues so that we don't bother moving the unmovable one, or the stable one in this case, right? Keep that one fixed. Don't bother trying to change it. It can't be changed. Just move the unstable one. So design strategy. Don't bother shifting the stable eigenvalue. Of A at negative 0.5. It can't be shifted. Instead, just worry about the unstable eigenvalue. Instead, design F to move or shift the unstable but controllable eigenvalue at 1. Okay? And so what that's going to look like is that in our desired polynomial, let's call it characteristic polynomial, in our desired characteristic polynomial, one of the roots is going to be this unmovable but stable eigenvalue. Okay, so that's the one that can't be moved at negative 0.5. And I think I've got a typo here. Z minus 0.1. Okay, so this one can't be moved. So this is fixed. Okay, okay, when I multiply it out, I get some desired characteristic polynomial. Okay, and now we have to solve the pole placement, or the, for the gains of F. So I'm not going to do that here, but I'll say that using the procedures from the notes, we get F equal to the following. Okay, so stabilization problem. We have solved the stabilization problem by using this notion of controllability, right? So again, at the end of the day, if you do have sensors for all the state variables and you want to stabilize this equilibrium at x equal to 0, what you need at a minimum is that the pair be stabilizable. AB be stabilizable. We have a test for doing that, right? So you can check whether or not it's possible and then design your F accordingly. If AB happen to be controllable, then not only can you solve the stabilization problem, but you can arbitrarily assign the eigenvalues of this closed loop system. Okay. So now we deal with the fact that in practice, you do not have sensors on every state variable. So let's see what that looks like. And so we move on to section 9.2, output, feedback, stabilization. All right, so now we're only going to assume that the thing that we can measure is, as in our usual setup, the variable y, or maybe the tracking error. But that's the variable that we have available to the controller. So let me just set this up a bit. So it is usually impossible or too expensive to have a sensor measure each state variable. And so therefore, so it is rarely possible, as a result, let's say, it is rarely possible to implement a state feedback controller. And so, as you know, normally the only thing you have available to you is modeled by y, this plant output. And so, how do we deal with this? And this is where we're in this section, we're going to deal with it by introducing a concept called an observer. So this is where the concept of observers come in. Right, to deal with the fact that we do not have sensors for every state variable. And the idea here is that one uses an observer to estimate the plant's state using the information available from sensors that measure the actual output. To measure the output of the plant. Okay? And that's what we're going to deal with in this section, right? So we don't have sensors for all the states, we just have a sensor for the output of the plant. Okay? And so the picture in the output stabilization problem is the following. And I'm probably going to run out of time, but I'll draw it again next time. So instead of having x available to us, we're going to have y. Or in our negative feedback, it would be negative y, but and so this will be our controller. This will be our plant. And we're doing output stabilization. So we're trying to get a stable closed loop system, but now we're only measuring Y. I've put the negative feedback there, but you could absorb it into the controller. The 0 here is indicating that I've turned off the reference. Right? I'm just looking at stabilization right now. We talked about this in chapter 6. We want this system to be internally stable. So the problem we're going to consider, and I've run out of time, is that if you give me a plant model, find AC, BC, CC, DC, so that when I hook them up like this, the closed loop system is internally stable. We will solve that next time. Okay, so I'll stop there, and I'll see you tomorrow. If there are any questions, I'll stick around for a minute.